Okay, so today we only have to do one important thing because the rest is tying up the clustering stuff. Your homework 2 will have a second part. When is this one due? When we say it's due? Tuesday. Next Tuesday? Okay. So Tuesday is what day? 13th. 13th? Okay, so there'll be another one that's due in about a week. And for that one, we need to do hierarchical clustering and DB scan. DB scan will probably be a demo next time, but how it actually works. There'll be two problems on it. One is a toyish data, it's very easy to run. The other one is the real data. Hierarchical clustering I'm going to talk about today a little bit. And then before we move next week on, I want to talk a little bit about some fancier clustering methods. And we'll see, that's just a story because you guys can have no homework like it. So for hierarchical clustering, what did we say? These are my data points. Everybody have seen this before, I think, where things get linked together, right? So start with each data point we call a cluster. Group the most similar items. Rebuild. We have the K equal the similarity matrix. Recompute. Let's say update. Similarity. So when I say group, I literally mean take a bunch of those things, say some xi1, xi2, xit, and make out of these, make a new object, x new. That's a new group. Update the similarity, and then we'll loop until everything is grouped. Actually, let's make it more general. Number of groups smaller than something. You could say. So it goes as far up. I still say I have 3 groups. If I want to stop here, I can stop here. Okay? We all knew that, right? I mean, I think I've said this in class before, briefly, right? And I think everybody has seen this. Anybody knows the name of it? How is this called? This? Huh? Yeah, how do I spell that? All right? I'm not sure. I think that's the right name for it. So you should know what this is. Now, is this easy or hard? What's hard about it? So now let's talk a little bit about the details. Suppose you're going to implement this, which you are, right? Well, not quite. In this class, we'll try to be flexible. It's a union of CS and DS people, so what we're going to do for interesting things, we're going to say, go ahead and implement it. If it doesn't work, run a package. Okay, we'll be soft on it. That's what we're doing for one of the K-means, I think, problem for homework 2, part A, so to speak. You can see, right? Okay, so if you implement this, how would you do it? Like, where is the problem here? There's two things. One that I'm going to leave it more up to you, and one that I'm going to tell you what should happen. So when I group things, initially I start to 7,000 items, right? So what does it mean to group them? You could say, okay, mathematically it just means associate a map of those things. Say, like in K-means, object 1 goes there, object 2 goes there, object 3 goes there. If I have a map, that's a grouping, right? All objects that goes to the same spot, they are in the same group. But computer science-wise, how are you going to do this? Like you can think initially, okay, I'm starting with my matrix K, right? That is 1 to n times 1 to n. And it's for each element I now have ki1, ki2, up to kin. Those are the similarities or distances from object I to everybody else. Right? I would like to do something with this grouping, but then how do I reflect that in here? If I build a dictionary, I'm going to say these 3 items, 1, 2, 3, go to some group number 7. And then, remember I have to update the similarity matrix, right? So the problem here is that if these items goes to a group, they get replaced then. So they get replaced by this X mu. So I should perhaps say that in here. These items replaced items by the new group. So visually, where that happens when I decided to union this group here with, say, this group here with this group here. I don't have those groups anymore. I only have the bigger group. So how do I do that? Like with actual computer science. What's going to happen here is my matrix, my effective matrix, it won't be that big anymore, right? If I group those 3 items, say this was xi1, xi2, and xi3, now I won't have xi1, xi2, xi3, they're also here. So all these now become one thing. They become the group that got combined. So what I would like to have conceptually is an X new in here that replaces those 3 or 5 or 7, how many things I grouped, and an X new in here. And now every similarity on this line is K new versus whatever item I have here, J, right? So the similarity now is between this new group just formed and all the other points. So I'm not that good at programming. You guys are better than me. You're gonna have to figure this out, right? How do I actually write a hash, a table, a list, a matrix, something that will allow me to do this? Keep in mind that those might be 70,000 items. Right? It may be not so easy to do the initial straightforward thing with 70,000 items, right? We're talking about a big matrix that needs to be chopped off and grouped in many ways and all the way up. So think about you start with 70,000 and you end up with, say, 10 clusters, right? Suppose your final destination T is T equal 10. It means a lot of grouping to get from 70,000 to 3. Was a question?
So if you want to group together 2 groups, like So you need to actually go towards the individual constants of the groups and then look up that similarity.
So that's the part I'm good at. That's what I'm going to talk about. I can handle the math, so I'm going to explain to you a little bit about the update. I think that's your question. How do I update the similarity? That I can do, and you are the computer scientists. You have to figure out the data structures and the programming. Now, I think a lot of it is online, so if you know how to look for it, you're probably going to figure out. Matlab does it. I've done this with Matlab. There is a function. By the way, you should learn Matlab. I know that's not what we say in computer science, but Matlab is extremely useful of some things. Matlab has a function who computes the similarity of a matrix, called PDIST, for the people who know about it, and another function who does the hierarchical clustering called linkage. So these do it properly. Of course, I would like you guys to study the problem from a computer science perspective. So I think this, if you represent as a matrix, this could be a massive pain to deal with a matrix that has rows and now join the rows. Now, depending what kind of infrastructure you have, you might be able to say in a matrix, combine those rows somehow and then eliminate those rows from the matrix. Or maybe if you have enough memory, block something. Leave x1, x2, and x3 in there, just block those rows as invalid anymore, so later on I don't have to look at it. I'm not saying this is a hard problem. All I'm saying, it's a non-trivial thing to say group items from 70,000 down to how many classes I want. Now, I know you can represent the tree. Tree is no problem. If somebody tells you the tree, representing the tree, it's easy. But how do you keep updating this data structure that contains the data? I think that's going to be one of the things.
Like when you are combining like those elements, like do we pick one representative item or do we take the average?
Neither. So this is a new ID. So conceptually, it represents as an ID the data points under it. So it's a set, if you like, right? Yeah. As concept is, what is this point? This is a set of all the underlying points under it. But this is neither the average of the data points, nor the median, nor something like this. It's a new ID. Now, what he asked for, okay, well, fine, it's a new ID. What do I do with it? I need the new similarities. Right? This we're going to discuss in a second. What is this K new J? How do I do this? Right? So again, conceptually, the group is a new ID. If you really want to think what it is, it's a set. It's a set of all the images that went to that group. But it's not an average image, a centroid. So how do I update things? Well, one thing, before I go, one thing that might simplify things is to say, every time I'm joining items together, I'm joining two at a time. That may simplify your life, right? Because every time I'm doing my grouping, I only have to deal with two things that are grouped into one. It may not be the most efficient thing, but maybe that will simplify the way you write your program. Now, in terms of update, so I would like to think of this. Here's the item that I'm joining. So I'm joining group X new. Let's say X new here is a group of X1 and X2. Those are also groups. So I'm imagining myself in the middle of the program, and I have two groups, and I'm joining them. Initially, of course, all the groups are just one image or one document. Right? So here are my groups. Those are the individual elements. Another hint useful for implementation is that when I'm here, say here and here, I have those two groups. I don't need to remember all the structure under them. So in terms of representing this group, it may be enough to keep track of simply who's in the group. Right? As a tree, maybe I want to store that somewhere if I want to keep a log of how my algorithm works. But once I'm here, this is kind of what we call in Markov chain memory-less process. It doesn't matter how I got here. It matters that the following digits or images or documents are in this group. So when I say a group, I mean a collection of objects. It doesn't matter how they got grouped. Like this one was grouped first with this and then with that. At this point, I know all of them are grouped. And these are the other ones. So now what I had before the grouping was a similarity between anybody here and anybody here. Right? Because before the grouping, I had a full similarity matrix between my objects, so I had that. Right? So let's say this is a point here, P, and that's a point Q. Right? And P is in the group X1, and Q is in the group X2. PQ are data points. There are several options for how to do this. KPQ, that was the distance or similarity, maybe, between P and Q. Now I have to define the similarity between the groups X1 and X2. So that's before grouping. What does it mean to have, I have the distance function, suppose I is a Euclidean distance or cosine distance. I'll have to set myself what is the similarity between two groups, right? So there are the obvious options here. Typically, there is a mean version, a max version, and an average version. There's some other ones, but those are the three typical ones that people are using. So I think it's pretty clear what mean is, right? Or max or average. What is mean? The minimum one, so minimum will be from here to here, right? That's the minimum between them, right? The maximum will be the most far away to the most far away. That's the maximum. And the average, so mean is the mean between P, mean between all the distances PQ, with P in the first group, Q in the other group. Max would be the maximum between the things. So all maximum distance. And average is what? Will be, but how do I write that mathematically? I take all the distances or similarities, I say similarities, similarity between all PQs, right? So that will be a sum over all P in X1 and all Q in X2 divided by how many of them are there. But I can tell how many are there. It's, yeah, P is the element, so it will be the size of X1 times the size of X2. So by size, in here, I mean set size. I don't mean norm. This is a group, so it's a count. Nice. So far, so good. So you're going to have to play a little bit with this thing, because better distances, better averaging options work differently for different data sets. Right? So if I tell you, hey, this is 20 news groups, what's the right way to figure out the distance? Right? That's not a big deal. Now, how do I average things? So once I group, I decided somehow my algorithm makes a determination, group those X1 and X2 together, make a group out of them, right? So after grouping, what happened, I had some other object here, say that was a C, right? And everybody, I have a similarity from here and a similarity from here, right? Now, when I got to this point, I only had those groups, right? So I didn't keep track of everything that's inside the group, necessarily, in my matrix. So now, I had So I had in here a similarity between x1 and my object C, right? I had a similarity between x2 and my object C. And after grouping, I want what? A similarity between the new group, x new, and my object C. That will be true for any C, right? Any other item that did not participate in this group, whether it was one individual item or a group of few items, I want to recompute the similarity, which means I want to combine those things, make one group out of them, x new, and now I have to compute the distance between x new to everybody else. So in a matrix form, it'd be useful to somehow leave in place all the values that don't need to be changed, right? So what happened here? I had the line of xi, I have the line of x2, x3. Those things are gone because they are grouped together, right? But everybody else in here, from some item to some other item that's not related to those will stay the same, right? So since this matrix can be 70,000 by 70,000, I mean, there are more efficient ways to do this. You don't want to have to rewrite the whole matrix, right? If writing this matrix might take 10 minutes, right? Which it can happen. The first time when you computed, what happened when you computed for homework 1? How long did it take to compute this matrix? 5 to 10 minutes, right? But imagine if you have to rewrite it every time you join things. That will be a lot of minutes, right? So you probably have to think of the computer science part. How do I keep in place what doesn't need to change? Okay? I'm a Matlab-oriented person, so I think in terms of matrices. I'd imagine that for me, I'd keep the matrix as it is, and only somehow disable these rows. Maybe even use one of these rows for my new group. I say, okay, the new group, x new, will get in here instead of this one, and do something about that. I don't know. Now, how about the computation? Naively, I could say, well, so suppose I do average, right? This is the average version. This will be what now? It's going to be like in here, the sum of all the P or Q now are belonging to x1, x new. That's all the points x, p, or q from before. Similarity between these ones, let's say R. R is either here or here. And some point here, call it V. V belongs to C. Now I have to divide this by the size of x new times the size of C, right, to make an average. Again, if this is average. So further, if I am to write this formula down, there's the sum right there from all R in x new and V in C of the similarity times, I can further complicate things here to say, what is this? These are set sizes, so don't get confused between norms or something like that. X is a set of objects, so that's how many elements are there. Now, who is x new? That's combination means what in terms of count? x1 plus x2, right? The sum, the count in this new group will be the sum of the two. Okay, and that gets multiplied here. I don't have space on the board. It's x1 plus x2 multiply with the size of C. So where am I going with this? I would like to do this update on average case, but I'll go to min and max too. Min and max I think are easier. It's just take either that minimum or that minimum. But I would like to go somewhere that I don't have to recompute by summing up all the similarities again.
So how do we define the decision boundary with averages, with minimum and maximum?
Decision boundary?
I mean, like if you have a new point, so versus average, the threshold like less than average will, if you had a similar, if you had some other group, you would get the average of point V for with that group or similarity between that group as well, right? Now you have two averages, so how would you?
So the groups, maybe I didn't understand the question. The groups are already defined for me at this point. The groups are what came out from before grouping, right? So the groups are those three groups. And I've already decided I want to join those two somehow. Good so far? So now the question is, this new object has to recompute similarity to everybody else. Right? Now I know what points are. If you're asking about membership, why is this V in there? That's come from before. I didn't put V here. This comes from the previous group. Is that the question?
If there were other groups?
Yeah, there were other groups, of course. This is C1, this is C2, C3, and all kinds of other groups in here. So you're asking, why did I pick C1 and not C2?
Why did you decide C1 would go to X new and not to C3 and C2?
Right, so why did I group those two and not a different two?
If you have multiple groups and a new point, how would you assign that new point to multiple?
That's not how it goes. This is not a classification problem. It starts with all points being their own group. So everybody's in a group already, because it starts with everybody in its own group. And then somehow, by some criteria, I decide to join two of them. And then another two, and then another two. Everybody is in a group at any point in time. Now, if I decide to join two groups, that can happen, then I make out of those two groups one group. And that group instantly contains all the points in those groups. So it's really a bottom-up procedure.
I'm not following. How do we calculate the similarity between a group, two groups? As in, if we calculate similarity between 2 points, it would kind of cosine similarity, but when there are multiple members in
So we're assuming we have similarity between points to start with. We're not worried about that. It's either cosine, Euclidean, whatever. Then here's the similarity between groups. It's the average of all the similarities between one side and the other side. Or the mean, or the max.
we can take any.
Yeah, you decide one in advance. They're not just three. People who do this, they have very fancy ways of thinking about it. I would like to talk about that if you guys, but I want to first make sure we're all on the same page here. We can't go too far. Yeah? Are we clear? Maybe you need to settle a little bit on it?
I can take this offline.
No. So your problem is, I think you're thinking more classification. There's no question here if a point comes in, what group does it go? That's not the issue, because everybody starts in a group. Groups get joined together. And when you join, you just put all the points in that group. But of course, you have to maintain the similarity function between the groups. Initially, the similarity between the groups is just the similarity between the points, right? That's my original K matrix that I start the computer homework one.
We are joining two groups, like if they are both similar, that's why we are joining them, or like?
Yeah.
Like so if there are three groups, we will join the two groups which are both.
So I grouped maybe that was not clear here, most similar groups. Now I can do this faster than two at a time if I have a procedure that detects, hey, these four groups are all very similar. If I'll be good at programming, I could group all four of them, right? I mean, the algorithm doesn't mean you have to do two at a time. If you detect some of them are extremely similar to each other, you're welcome to group them. But of course, you have to update properly the data structures you have. Now, 4 or 3 or 5 items or 5 groups get together, you now have a similarity between the new group and everybody else. Because what happens when I group things, I don't have those items anymore, right? I have the group. I need to know the group similarity with this or this or this, whatever else got grouped, such that I can decide what to group next, right? Once few items have been replaced by a group, it doesn't make sense to compute a similarity between here and the items anymore, because those items, it's like a hard decision. Once I make the decision to group them, I'm not going to go back and revise that decision. So now I have to deal with this as an item, which means I need similarity from here to everybody else.
If you say you are not concerned with the items once the group is formed, then while combining two groups, wouldn't it be just two items and not the items inside those groups?
Not sure I understand. So, well, a group is a set of items conceptually. If I have two sets and I decide to join them,
You will have another
with
of
the set that's a union of
Yeah.
them. So that's more than two items,
Yeah.
right?
Okay. But then when you say that you are not concerned with the items inside the group.
No, I am concerned with the items inside the group. I'm not concerned with how the grouping happened.
Okay.
Like, how did I get to this group here? Was it this grouping that way or the other way? It doesn't matter. The moment I decided to make that group, it only matters what are the items in the group. Now the group, we can give it a group ID. If this is 1 to n, maybe the group is n plus 1, n plus 2. That's up to the implementation, how you want to handle those groups. You're going to need to know that this group ID, Virgil, contains the following points. Because in hierarchical clustering, you want to be able to cut this tree somewhere. And when you cut it, that's going to give you the partitions, right? So suppose I cut it here. That's a standalone partition now, so I need to know who's in that partition. Now, for the purpose of moving forward, all I need is the similarity between this new ID and the other ones. Yes, you guys not gonna let me go to anywhere interesting here.
So we are computing the similarity between the groups.
Initially, it's between the groups which are the items.
So like as we keep on merging the groups, combining the groups, so we are again computing the similarity. So are we computing the similarity at the same level in the groups? Or
So you need to maintain, if those are your current ones, this current, let's say this one didn't get grouped, it's current, current, this is current, right? Current and current, right? Let me make it more clear. These are my current ones. This is what I grouped so far. It doesn't matter how I got here, again. Something happened, I got here. This is a group of things, those are individual ones. This is a group of things, maybe more things, and this is a group of many things, right? What I need to have to move forward is the similarity between the pairs of the current ones, right? I don't need a similarity between this one and individual items here at this point because those items are not in the play. They got replaced by a big group. So I have this current schema. Now suppose I want to group those, say I group these two together. This is my new group here. I need a similarity between this and who? The other current items, right? I don't need a similarity from here to here because this one is not an item anymore, got replaced by a group. But I need a similarity between here and here, 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 and here. Right? I always need to have the pairwise similarity between the existing groups. So I used to have it again, my current groups were here. This is not a group. Here, 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 here. I have those 1, 2, 3, 4, 5, 6. Now those two got merged. I need a similarity between the new group and the other 5.
How do you make the first group? Like, I mean, we know that we find out similarities. So,
Most similar.
so any two which are most similar, any 3, any 5? Or
You can do it any 2. That would be a simpler version, but I think those can be replaced by a fancier version that's any 3.
like this one wouldn't work with any 2. Like then the first 2 would be a group, and the second 2 points would
Why
be a
wouldn't
group.
work with the first 2?
So just looking at the bottom points, any 2 points would be a group. You wouldn't have standalone points after the first group.
Of course, I have. These 2 gets grouped here.
Yeah.
These 2 get groups here. Now this point gets grouped to those 2. Right? This is an individual point, gets grouped to those 2.
But shouldn't it get grouped with some other similar?
You always group whoever's most similar. This point might be more similar with the group of 2 or 3 or 5 than it is to any other point.
But at the first iteration, you would only have first layer. Of
Yeah, but
groups.
so this is not a batch process. You imagining a schema where it's like a tournament. Every team must play every other team. That's not the case. Okay? The first two teams play, they get joined together, and now that's a group. Two teams might play separately or may play against this winner from that game. Okay, so I don't have to have a tree that goes, like this, nice and smooth all the way up. Maybe I get those two combined with this, and now those two got combined here, and then combined with that, and then those two get combined, right? I mean, when I say groups in general, once two things got grouped, that replaces the existing items into a group, and now that group acts like a new team player. Yes.
Just to be sure, so
It's good we have some extra space in our lectures, so because we can't seem to get very far.
So you are using the group items to calculate the similarity for the group as a whole. Then it acts as an item to find out the most similar.
So I need now from that new group similarity to the other existing groups.
Groups or item as a whole.
Yeah, I'm gonna think everybody is a group.
Okay.
Even from the beginning, I'm gonna say every item is its own group. So from now on, everything is groups. If things get together, that's another group. I won't have items anymore. From the very beginning, everybody gets to be their own group. Every data point is a cluster or group. You guys never seen this before? This dendrogram kind of thing, hierarchical clustering? I mean, this is a popular culture thing. It's not coming from clustering from math. This is from all kinds of population and species and how things group together naturally. The idea of this, it's not a mathematical one. Okay. Back here. Can I do this faster than resumming things? So where am I? I've got a bunch of groups, and I have the similarity between any two of them. That's what I need to keep track in my data structure. The current groups, what's their similarity? So I can decide which two, or if you want to be fancy, which 3 or 4 or 5 gets grouped together. I would say do 2 at a time to make it simple. Now I have the similarities. I decided to group those two groups. Fine. For some criteria that says the minimum similarity between your existing groups is those two. Now, what do I have to do? I group them, so I need to update my data structure, keep track of IDs, but I also need to recompute the similarity from the new group to everybody else, to C1, to C3, to all the other groups existing here. If I do the average, I'm looking at this and say, hey, the similarity between the new group and C is the average of all the distances between any V and Q or any V and the P from here, right? So those are all the distances summed up, divided by sum of x1 plus x2. Those are the sum, this is the sum of the new group, times the size of the whatever group I'm computing the similarity with. Now C didn't change. This C is the same as before. Only those two got merged. So my simple point that I'm trying to make here is how do I do this without recomputing the whole sum? Is there a way to kind of update from the previous values? Can I say, I knew the similarity between this group and C. I had it. This, I must have had it somewhere. So where is it? I used to have, so I have already the similarity between x1 and C, and I have the similarity between x2 and C. Because I must have had those things before grouping. I had the similarity between any two groups. Now I want the similarity between the new group just formed and C. My point is a simple update here.
You multiply with the size of x1 there and size
Okay,
of
so
x2.
what is it?
So similarity of x1c into size of x2.
Similarity of x1c
Size of x2.
times size of
Plus
x1
similarity of
plus
x2c
similarity of x2c
into size of x2 divided by size of x2.
Maybe it takes a second to figure out that this is true, but it is. Right? If you think about this sum, it could be written that way, assuming I already have this similarity between the group before. which is as I go up and up and up, the groups become bigger and bigger and bigger. It's a lot easier to do this than to recompute all the sums. Okay? How about mean? If I don't use average, I use minimum. So I had the minimum distances between groups. I decide to join those two groups. What's now the minimum distance between the join group and this one?
The minimum of
I look at them both minimum. What was the minimum from here to here? The minimum from here to here? And the minimum of those two will be the new minimum. That's easy to see. This is a little bit harder to see. So in the homework that's coming, you guys are going to have to implement hierarchical clustering. And you could be surprised by how long it takes you to do it versus how long it takes Matlab to do it, for example. Because of the data structures, that's something you really want to think before you start writing the program. How do I maintain the groups? And because if you use average, you want to do something like this. But that's, once you see the formula, that's an easy thing. All right. So I would like to show you some things now. Let's see how far we get. So what I did in Matlab, my program for computing hierarchical clustering has 3 lines, okay? Because I use the following lines. So what did I do? Maybe make this a little bigger, you guys can see it. I don't know how well it worked yet, I don't have an evaluation. So I've read the data. This is the MNIST data, I think, something like this. I've read the data, and then I say, what's the size of my matrix there? That's the matrix, everybody knows that by now. And then I did this. This in Matlab assumes every row is an observation, and the columns are the features. So then what this does, computes the similarity matrix, pairwise similarity matrix PDs. It writes it in a vector format, so the end result D is a vector as opposed to a matrix, but Matlab knows how to make this vector back into a matrix if you want to. So you can ask for things like size of D, it's what? But it's 1 E at plus 9 means what?
1
Billion? Is that a billion here?
Yeah.
Times 2, it's 2.45 billion entries in this matrix. That's probably just half of the matrix because it's symmetric, right? Kij is Kji. I think it's just half of it.
Compute it within like 2 seconds.
What?
Did it compute the whole similarity matrix in 2 seconds?
No. That took a while. I didn't compute it, I just show you the size. Okay? This D is big. It's like 9 gig. I still have my computer has 16 GB of RAM. I used to have a workstation at home that currently is not working, so it's pieces on the table. But The funny things about the modern operating systems, if you pay attention to them, I think this is the latest Mac OS 6, I'm not sure, is that even though it's 16 GB, you may see occasionally things like 18 GB allocated, and no crash. Why do you think that is? They compress the memory, right? So they compress it live. The hard drives too. The files, as you open files and write them down, they compress, decompress. So it's quite likely that if you have 16 GB of RAM or the modern operating system, you can actually use maybe 20 as far as Matlab is concerned. So that's nice. So then what did I do? I did this. This linkage can work directly with the raw data function, right? Or can work with the D. It knows how to figure out whether you call it on X or you call it on the D, which is the distance pairwise. I didn't do it on X because if you call it on X, it internally calls the PDIS to find the D, and I already had D, so it's better to do it this way. This one took shorter, but this whole thing lasted less than an hour, certainly. And then I can have the size of D here, size of Z. This is an internal format to keep track of the tree. Z will have all the hierarchical clustering all the way up. I'm not saying you have to use Matlab. I'm saying that's what I've done here. And then I use a dendrogram to try to plot it. So I try a few things. In 500, it gave me this. Really, I can't really see it. This is supposed to be this tree organized in a certain way, so you know which got grouped with who. It truncates the bottom if this parameter says how much of the top of the tree you want to see, right? I try 50,000, can't see anything. Let's try something easier. Let's say we want 50. I don't know how long it's going to take. So the Z is the internal structure of the whole hierarchical tree. Now, how much you want to display in a dendrogram, you give this parameter. And in here, it displayed how things got grouped. Of course, you need to have the IDs to see who got grouped with who. But this dendrogram is this tree right here. So in Matlab, these only take 4 instructions, the whole thing. I don't know if it worked though. We'll have to evaluate the clustering to see. So the point of this is that if I want to cut it somewhere, I'll get a bunch of clusters now. Hierarchical clustering goes all the way up. I get a bunch of clusters, and now I have partitions. I can evaluate them the same way I evaluate partitions from k-means, right? Okay. So that's one thing. Here's another thing that I wanted to talk to you about. So now we're done with the technical stuff for clustering, except a demo for dbScan coming next week, because you're going to have a problem on that. But there's a lot more than those basic methods. So I have some slides here. Those are actually from a professor at CCIS, not me, but somebody else. Mirek Riedewald, maybe some of you know about him. So what happens if the data is very highly dimensional? People have struggled with this problem a lot, and we have good answers in 2 ways for that. We're going to talk, that's what we're going to talk about next week, data dimensionality and reduction. One way is to call a dimensionality reduction function. Most common one being BCA, right? If that works, great. You should definitely do that. By works, what do I mean? A dimensionality reduction takes the data from 100,000 dimensions and represents it into 30 dimensions, or 20, or how many you want. If you manage to do that, not losing information, we'll define next week what not losing information means. Like you preserve distances, for example. If I have two images or two documents or two people, and I had a Euclidean distance between them, say, or a cosine distance, I had a pairwise of distances. It's a well-known thing that if I preserve all distances, even though I represent my data now in 20 dimensions, I can recompute distances. If I preserve all the distances, we call that gold, like perfect. If we could do this for some data sets, that's great. We should absolutely do it, but it requires some property of the data. If the data exists in 784 dimensions, and we manage to represent it in 20 and preserve all the distances, it means algebraically it's very weak matrix rank is very weak. So that means that the data, if you want to visualize it, does not live in all 784 dimensions. It lives in a very small subset of those dimensions. So if that happens, it's a property of the data. Definitely a dimensionality reduction is the right thing. But it doesn't happen that often. So in some cases, like in 20 newsgroups, for example, it's hard to reduce dimensionality without losing information. In particular, because dimensionality relates to words, right? And every word is somewhat relevant, very little for the whole group. If you take a rare word, you could say this word is almost irrelevant. It only affects 0.001% of my data set. But every word affects that many. So if you decide to take out words, the moment you take a consistent number of words, like say half of them, then you lose a lot of information, right? So for text, people have come up with different strategies. A lot of those are discussed somehow in the information retrieval course. But then people have thought, okay, can I start thinking about clustering in really high dimensions? How do I do that? So the algorithm presented here has to do with that a priori algorithm that I think you guys did for homework 1. So what happens here? That's not the one. Where is it? So I can start in few dimensions. How do I pick which dimensions? That's a interesting question, but I can start in few dimensions. And I could say, cluster the data not in 100,000 dimensions, but in 100 of those dimensions. What would I get? I get some notion of similarity that's only valid in those 100 dimensions that I picked. It may be that those 100 dimensions are not necessarily part of the original 100,000. Maybe I run PCA and I do some initial clustering in there. You remember how this a priori algorithm used to work? You start with co-occurrences or things that are common as a factor of, as a length of 2 windows, and then you take those as a base and you try to add candidates for the next one. We can try to do the same thing here. We can say do a clustering in some initial set of dimensions, and then given that clustering, try to do some candidates clustering. Say, okay, if those items are similar and these items are similar and there's some similarity between them, these are different groups, different dimensions, right? So I do it in 3 dimensions, I do it in a different 3 dimensions, and now I say if there are common items between them, maybe they are similar in all 6 dimensions. Does it make sense what I'm saying? Say I pick 3 dimensions. I say group the similarity or partitioning, clustering with k-means in those 3 dimensions. Now do it in a different 3 dimensions. If I see common items between those clusters, maybe as a candidate, like in a priori algorithm, remember we form those candidates and then we prune the candidates, right? Same thing in here. Maybe we can form some candidates and reevaluate that clustering in 6 dimensions.
How can we prune so as in if let's say in the initial dimension there are not many similar points, so when we go to the higher dimension, how we prune say these are not similar,
so by prune, I don't mean something technical. I mean we form a candidate clustering, and then we'll have to evaluate that in all 6 dimensions. like in a priori algorithm, we use the previous step to create candidates that are possible clusterings for my new step, which is 6 dimensions, say. And then I have to evaluate to see which ones are actually correct in 6 dimensions.
But then we also do the items which are less than threshold, so similarly.
I think when we create clustering, the idea is to create partitions, not objects. So we won't have, I think we have to evaluate different partitioning, not different objects. So I don't know why you think we have a point outside the partitions, because everybody's in a partition.
Maybe I'm not able to do so as in let's say 6 dimension partition the data. Let's say we find that cluster 1, so cluster 1 is the group that we are interested in because they are most likely similar. Then we go to let's say higher dimension, 15 dimension. So how do we use this information to calculate the?
Right, so we have to do it in more than one of the 6 dimensions, right? I have this done, this partition done in 6 dimensions. That's all the points. And now I have a different partition done in 6 dimensions because they're at different 6 dimensions. Now my job is to evaluate if I can, how do I determine a clustering that works in both 12 dimensions combined. So just like a priori, I mean, this is an idea. I'm not talking at technical level. Just in a priori, we use the previous stage to create candidates, right? So how would you create candidates? You look at the partition in 6 dimensions and look at the partition in 6 dimensions. If you see common elements between them, you say, why don't put it together? That maybe it's a partition in 12 dimensions. There is a good algebraic reason for this. So I want to give you just a hint of the idea. This is not part of the homework. If you look algebraically at the data, everybody that's similar in many, many dimensions would be similar in any projection. The theoretical value of this comes from that reasoning. If 2 items are really close together, no matter how you project the space, they will be similar in the projection. So what this is saying is that no matter how you pick 3, 4, 5, 10, 20 dimensions, items that are truly similar in the original space of many, many dimensions, when you project everything on 2 dimensions, or 3 or 5, all those items must be similar. Now, that's nice theoretically, but in practice, they document. If I pick some words, right, most documents won't have these words. So if I only pick 3 words and I'm doing similarity in those 3 words, all documents that do not have those words will end up very similar because it's 0, 0, 0, 0, 0, 0, 0, 0, 0, no similarity. So in a case of sparsity, while the idea is still correct with projections, it doesn't mean we'll actually give you something useful. But in general, the idea of doing a projection and evaluate similarity in a projection and repeat the process, do it many times in many projections, and if you get a consistent value, meaning me and him are similar no matter how we do the projections, that's usually a strong indication that me and him are similar in the original space. There are algorithms built like that will decompose the space to dimensions. Now, even that decomposition is better to not be random. You don't want to pick 3 random dimensions. It doesn't work so well in sparse data, but I think on matrices like the MNIST kind of data would work reasonably well. This is also related to the idea of visualization. I can't visualize high dimensional data, but I can visualize it in a projection, right? So then I have the same issue. If I choose a projection, how do I know that projection is good? It may make sense to choose several projections and visualize it in, say, 2D or 3D, and then see if what I observe is consistent about it. Yes?
So if you mean to say that in multiple projections you try to visualize the data, so if the data points are similar, then in all those projections, the projections would be similar.
Yes. Any 2 data points that are similar would be similar in any projection. Again, that makes more sense in a non-sparse state. So if I would choose PCA dimensions to do the projections because PCA dimensions are linear combination of the original dimensions, right? but it's based on this fundamental fact that two things that are similar in projections. Keep in mind that that's not reciprocal. If two objects are similar in a projection, they're not necessarily similar in the original space. So that's one thing. The other thing that I have here, that's not it. The thing I have is here. I'm going to show you this because I want to show you the graph without drawing on the board, but then I'm going to talk about this on the board. This is a generalization of KNN that works in both supervised and unsupervised learning, and it has quite a few names on it. Density estimation, heat equation, kernel equation, density kernels, weighted averages. So some people at Carnegie Mellon University, at some point, that's probably about 15 years old or so, figured out how to formalize this whole process. This is the supervised learning notion, and it's easier to explain that way, but then we'll do some equations on the board. So here's, by the way, this is a big topic now, which we're gonna do after the spring break in graphs. In graphs, social graphs, there's a lot of data mining going on of these graphs, I'm sure you know. One of the biggest items we study in this class for the graphs is community detection, which is a fancy name for something you already know. Because in a graph, if I have edges like friendships on Facebook, right? Those are not just good, are 0, 1, right? Friendship on Facebook is a 0, 1 notion, is a black or white thing. Graphs are a lot easier to work with when edges are 0, 1 than when edges are, you know, gray. Like, I'm not so friends with you. Maybe I know you, but I'm not really your friend, kind of thing. So the moment you move from graphs that are hard graphs, 0, 1 edges, community detection is nice and easy. Suppose now the edges are not 0, 1. They are some level of friendship. That's a much harder problem to determine a community now. Okay? So, but that we're going to study later on in the course, how community detection works. But it's, if you know about community detection, I mean, not the algorithm, but what's about, you know, to figure out, okay, all these people on Facebook are friends with each other. In graph notion, that's from a clique, right? It's like everybody seems to be friends with everybody here, so we need to know that. Those are the initial, a lot of people working at Facebook in the early years of Facebook were working essentially on community detection. Of course, they want to make money, so they're interested in what ads to serve to what community. That's the biggest deal for Facebook. But community detection, it's important in social networks in many ways. So now here's what happened with this paper, which is, again, done for supervised learning. Let's assume we have a graph. The graph is between my objects. So those are the MNIST digits. Those are the 0s, 1, 2, 3s, right? Now, we think of those images as IDs in here. I want to ignore the label for the moment. Of course, I know this is a 6, and this is a 0, and this is a 9, but they're just IDs, right? x1, x2, x3. I create this similarity. This is exactly what you've done for homework 1, right? We computed a similarity between them. Now, what this paper is doing a particular similarity. This. It's a Euclidean similarity, right? It's the sum of the different squares. But it's divided by, this is the variance on that dimension. So you look at a particular dimension in data, some column, and all the distances in that column are normalized with the variance on the column. And then it's exponentiated. Exponential makes gaps much bigger gaps. So if two things are a little bit non-similar, in an exponential sense, they appear a lot more non-similar. So where they get this from? They get this from physics. This is how thermodynamics work. It's called heat equation for a good reason. Heat acts this way, temperature acts this way in terms of distance. How much the temperature changes from here to there, it uses a function like this. So this is a similarity. This is what we call Kij. And as a function of distance, this is modeled from physics for thermodynamics, which that's why this is called the heat equation or the heat kernel, if you like. Okay. That makes the math works easier, but a lot of what we do with this similarity further applies to any similarity. So what do we have so far? We have a similarity function which is particular this equation, and we build a graph. You can imagine building the MNIST graph. Of course, it's a very big graph because it has 70,000 items, and the edges are the similarities we just computed. Then what? Then we say, we want to minimize this. Now, if you think about this, this is very similar to the k-means objective, right? It's saying the function I want is a sum of, this is how similar things are. But these are, instead of being a point minus a centroid, these are 2 points here. So what is this process trying to do? Is to try to find this function f for each point. So I want a function f that minimizes this function. What's the idea here? Is that if this wij is high, what does that mean? Things are very similar. So for similar things, I want f to be very close, right? I want the difference. So think about me versus him, right? If wij between us is high, that tells this you want f to be very close, the difference to be small. Suppose this is f is the salary. If we are very similar, we want the salaries to be very similar. If wij is 0, meaning I can't tell if 2 points are similar or not, I want f to be, it doesn't matter, right? I can allow f to be anything because the difference between two things that are non-similar, it won't affect this objective because it's multiplied by 0. What happens if wij is -1, very, very dissimilar? Right? The similarity can say, suppose can go the other way, make it -1. In that case, I would like the f's to be very, very different, so the difference is big. So I don't want to talk about the mathematics of it, but what this is saying, similar things should have close f's. F is the function that I'm trying to infer here. Non-correlated things, doesn't matter. You can assign any f you want to them. And very dissimilar things should have very different f's. This is how energy works. If you turn any room, like this room, has sources of cold and heat. What are the sources of cold in this room right now? Where's the cold coming? The windows, right? The doors, right? Maybe the AC if somebody turns on. Where's the source of heat? Maybe we don't have one here. We are a source of heat, certainly, right? And the radiators, if they're radiators, every room has sources of cold and heat. Now, in a room, when I start the room, the temperature is not in an equilibrium state, right? But if we stay in this room with the same windows, with the same coldness, with the same heat, and with us here, eventually it stabilizes, right? We all know that at some point the temperature in a room becomes stable. In thermodynamics, that's an equilibrium position. It turns out that equilibrium is the minimum of this function for heat. So in other words, this is called an energy function, and every time the heat stabilizes, like anything in physics, it finds an equilibrium position. And equilibrium means it's minimizing this function. The lowest energy. Do we remember any physics from high school? No? Okay, so F is the temperature at different points. what in the physics model, who are the I and J? Window, radiator, you, him, me. Every point in this room is an I and J. Every point have a Wij. Wij is how similar 2 points are. It comes from here, from that function. How far apart are them with an exponential. F is the temperature. And it makes sense, right? The temperature for very similar points in an equilibrium position would be very similar. But for far away points, might be different. So people took all this from physics and figured out, we know that the F has to have a very nice property, which is exactly the temperature property. We should write that on the board. I think it's written here. Make this bigger a little bit. This answer is what makes this so interesting. This answer, which is exactly the temperature behavior, actually works a lot in data science for a lot of data sets. What this is saying, it's saying the temperature at any point has to be the weighted average of the temperature of the neighbors. This equation makes it so suitable for any graph. So what is actually exactly saying? I mean, we can take a look at that graph index. Saying that if I have a point and its neighbors, this is the point J in this equation here. Fj has to be 1 over degree of J. We'll talk about degree in a second. Sum of Wij f of I. Fi. The dj, this degree, is a weighted degree. It's just the sum of Wij. So this is nothing else than the sum of Wij for any neighbors times, it's a weighted sum. So this D is just the sum of weights, I believe. We'll have to look at the paper, but I'm pretty sure that's what it is. So this is effectively a weighted average of the neighbors. Again, it comes from thermodynamics. In physics, this is what happened. The temperature at any point has to be the average of the points around. There's no other way if it finds an equilibrium position. But this is nice because now it works in any graph where I can compute Wij. This is I. There was a question? So this property here, I think it comes from a theorem that says the function that, you can prove this theorem, it takes a little bit of math. The function that minimizes this equation must have that property. So that's a mathematical statement that says if you want to minimize that equation, you obtain this kind of function. Now this is not an answer. See, this function is defined on itself. So it's not like it tells you how to compute it, but it tells you that f must have this property, which is called, I think, harmonic in a graph theory sense. So any function that has this nice property, the function at the node is the average of the neighbors. It's called a harmonic function. And without doing the math, maybe you believe me that any function that minimizes that, I mean, it finds the equilibrium position, will have this property. So now, why is this so useful for data science? First of all, we ignore the heat properties, and we can apply to any graph for which I have a similarity. One. Two, this can be implemented quite easily to obtain a supervised learning algorithm. So one thing mathematically that doesn't work with those f's, f's are up to us, right? F is a variable there, and we have to find it. You could say there's a trivial way to minimize that thing, right? When f equals 0 or constant, we'll minimize it, say. So it needs what's called a scalar or stability or regularization condition. In unsupervised learning, we put that condition. In unsupervised learning, we need that condition. In supervised learning, what we can do is to set F to the knowing labels. That's what those people do in this paper. They say, in order to not have a, we have a training set, we know this one's a 1, so the F of this point is 1, F of this point is 0, F of this point is 9, so on and so forth. So now I fix these Fs for the training set. So if you think now about the equation, I can't get a constant F because F is nailed down for the points in the training set. It cannot move. I'm not allowing it to move on those points. I'm only allowing it to move on the other points. And then what happens here, they have these nice mathematical equations, how to compute Fs for the other points. Assuming you have a training set and you fix the F of the training set, that's not allowed to move. Then how you compute F for all the other points to have this property, average of the neighbors. Now, it would be easy if everybody would be an average of neighbors that's already labeled, right? If I take a point and I know this, and that, the F's for this value, the average is very easy. But you see what happens in this graph? Almost everybody has unknown neighbors, right? It's like PageRank. You can't compute the value before you know the neighboring values. So they give these algebraic methods here, how to compute F's for the points that are not labeled. Turns out that this stuff doesn't work. So I mean, they did this math and it's all correct, but you can't do it in practice. So even them after this paper wrote, okay, well that's correct, it can possibly be done like that in practice. We need to implement an optimization strategy, and they came up with a much better idea to compute this after that. Now, what do we do for unsupervised learning? We have no labels, right? Say. In there, we need a condition. That's written in your book at chapter 6.7, graph-based algorithm, in the Agrawal book. So they discuss exactly this idea in there. We want the same thing. We don't have labels. There is no blue 1, 0, 9, nothing. But we do have the weights, right? So we know how similar objects are. We want to spread this F. So in that sense, this is very related to another big subfield of data science. F is an embedding in one dimension, right? F maps each point into a value, because this F is a score or a value. That means now I embedded my data points into one dimension. That's not good for a representation. You cannot possibly hope that these documents or images can be written in one dimension. Everybody has a value. But could be useful for some specific task. I want to know how sick people are, right? Sickness, maybe it's a one-dimensional thing from 0 to 100, you know? I want to know how likely it is for my students to graduate. That likelihood is a number, right? So for things like that, it makes sense to try to think of this as an embedding. Embedding is a huge subfield of study of how to embed points and data and ordinal data, so far as so forth. There's a lot of geometry going on in there. We need a regularization condition. So what happens here, we need to compute two things. So we have this D, which is a diagonal of sum of Wij. And we have L is D minus W matrix. This is called the Laplacian of graph. So W is the Wij matrix. This is called Laplacian. You don't have to worry about the name. And the condition on F scale condition is that F transpose as a vector df is equal to 1. That's to prevent, otherwise of course it cannot be optimized. Like we said, you get a constant F, that's the minimum. So there's an interesting mathematical phenomenon that happens here. If I choose things nicely, and they're chosen nicely, I get F computed as an eigenvector. That's not different than how they do it in this paper. We all know now, the paper doesn't, the book doesn't mention this, but you can trust me, algebraic methods don't really work that well. Like, that's why these people done the math with linear algebra and then figured out, okay, that doesn't really work in practice. The book doesn't say that. It says compute eigenvectors, blah, blah, blah. But if you do that, it won't work. The reason it doesn't work, I don't know how I'm doing with time here. Okay. The reason it doesn't work is it's not that it doesn't work, but when it works, PCA would have worked too. So every time linear algebra, in this sense, works very nice, you could have done something simpler in the beginning, and then everything would have been smooth after that. For example, 20 news groups, because it's a relatively small data set with a lot of sparse features, will never work with linear algebra strategies like this. But it's a nice theory. So people got prizes for this kind of thing 15 years ago. Best paper, award, da 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 da. It turns out it's not that useful, but still, it's a nice thing to know, because in data science, sooner or later, somebody will tell you about heat equations, minimizing in an equilibrium position, graph Laplacians, and how to solve it. How to solve it, you can read in the book. It's once you have this, it turns out this is a semi-positive definite matrix, so a positive semi-definite matrix that has enormous nice mathematical properties. We're going to talk about those when we talk about PCA. Symmetric matrices that have the property X transpose MX positive all the time allow for very nice decompositions into eigenvectors. So if we have those properties, the theory goes extremely well. Practice doesn't go that well. Right. So again, if these methods would work, you could have done something simpler earlier and solved it that way.
Clustering works on this idea.
I think it's very similar to this. Yes. I don't know the exact details, but I think it's very similar to this. And like before I said, if linear algebra methods work, this is for supervised learning, where we can do it unsupervised with some conditions. If you get the good result, that's great, but you could have gotten easier. Because in general, linear algebra doesn't work so well.
What does embedding here mean? Does it mean it cannot map?
Yeah, embedding means I embed some points into a k-dimensional space with some property. The one area that I'm very familiar with is ordinal embedding, where what I have about points is preferences. I like that movie more than other movie. Spotify, it's doing research right now into how to embed the songs. They of course have the songs, artists, genre, whether it plays violin or piano, all those properties for songs, just like Netflix have them for movies, right? Genre, actors, da 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 da. They find that these properties don't really correspond to people preferences. So it's an area of research right now for all these companies that says, if I take your preferences, you like that movie more than other movie, more than this movie, so on and so forth, and his preferences, and her preferences, and so on and so forth. Can I re-embed the movies in some number of dimensions, say 20, that are not the actors and special effects and music and so on and so forth, just to satisfy people's preferences? Exact question is, how many dimensions do I need for movies to embed them so that I can represent properly that you like that movie better than the other movie? Because it turns out with the existing stuff that we have for movies or songs, this doesn't work really well. So this is an active area of research. If you take an internship right now on Netflix or Spotify, you might be having this problem. How do we write new dimensions for data that satisfy preferences better than the dimensions we have? So that's an example of embedding. In embedding, we don't care what the points are. Like we don't know what dimension 1 means. This f is only one dimension. We don't know what it is. But we want to satisfy a certain property like this.
So like would an example of a new dimension be like explosions in a movie or something?
Typically, those can be obtained from the original data. It's just a combination of them or a filtering.
Yeah.
The ones that cannot be obtained are funny combinations. There's something in the movie that can be expressed with explosions and this and that, but there's something in the frame or in the sequence that people feel for somewhat emotionally, say, and it cannot be represented purely by what's in that image. If I tell you what it is,
So it's combining a bunch of different factors into a new factor.
so that's why these companies put money on it, that because they think people have a perception about movies or songs or maybe, I don't know, products that cannot be simply represented by describing in an enumerative set what that product is. Especially for art, this is true. If I describe a painting by what's in it, you're gonna have a hard time telling how much you like that painting before you see it. You know. So I think there's a relatively new field of study. How do we map people's perception of objects rather than just enumerating what's in them? Of course, Netflix doing a combination. Their algorithm for recommendation uses both their internal embedding features and whatever they know about the movie. There was another question, sorry.
I was just wondering, how is this different from
Compression,
compression?
well, we can't answer that in a few seconds, but compression really it's a matter of rewriting what you have. Take zip, right? Zip what says if your data has a lot of zeros, instead of writing 17 zeros, I'm going to write 1 and count 17. So it's not really re-embedding, it's just saying, let's not write 0 17 times, or an image, right? An image is all black. I can just say black from here to here. It just most of the compression do that, you know, the ones that are being very used. I don't know if you have something else in mind, like MDS or?
Yeah.
Right, I think we have to take that offline. But most of compression schema, it's optimized for rewriting what you have more efficiently, not recreating new dimensions. All right. Next time, dimensionality reduction. Oh, sorry. Like always, I forgot. Yay! 3 weeks.
How do we work around it? Knock it over.
Yeah, we still have homework.
You're saying you're going to run out of my stuff?
Oh, yeah. Sure. Sorry, guys. Let me pack up this camera really quick. So you have a space.
Use the